Okay, so now we have the area. Oh, let's see. We have the shear stress required, right? That we got from the ultimate stress in shear. That's the point we know this material will fail, 16 KSI. And then we calculate, okay, what's the area that we are shearing, right? And that's just the perimeter of this object times the thickness. It's this area here, right, along the edge. So now we have that area, so we can calculate the force. That's just equal to the 16, I guess I use 16,000 pounds per square inch times the area, right, which is 1.144 inches squared. And this gives us 18,300 pounds. So you need to, this is the force you need to apply, right? Force required to punch out shape. Shape is. I was thinking minimum, right? That's the minimum force required to punch that shape out of the aluminum. So this is how you'd use this shear information to actually figure out, because you know, in the first chapter we're doing these calculations, we're like, oh, you know, I don't know, that's the shear stress, but what does that really mean? Well, now you compare the shear stress to the ultimate stress in shear, right? And now you can say, okay, am I below that shear stress? Am I above it? What force do I need to make sure I am above it? And that's the force you're going to need to punch out this shape. All right, so let's go back to the slides here. And we're going to start talking about torque, because this is going to be important for rotating shafts. And you guys all learned about torque in the TC 120 class, because it's basically a moment, right? It's a force times a distance. And that's what that is, right? We've got think of a torque wrench, right? We're applying this force at the end. Now, no one actually grabs the torque wrench from the edge like that, but typically your force is going to be applied the center of it somewhere in here, right? And you've got a distance that you're acting over. And you know, the wrench here, say you're applying 50 Newton force and it's a 250 millimeter distance, right? Your torque is what? 50 Newtons times 200 millimeters, and then I'm going to convert it to Newton meters by oh, this is weird. Apparently I put the wrong numbers in here. Yeah, so I found another mistake in my slide. This is 250 times 50. Yeah, so this is the correct answer with 250 millimeters. Yeah, so that's the torque, right? It's a length times it's a force times a distance. It's basically the same as a moment, except with torque now you actually are moving, right? And torque, you can use torque to get power. So what is power? Well, power is how quickly you transfer energy, right? And you know, the metric unit for that is joule. And here we've got you know, joules per second is power, right? That's a watt. What are you talking about? Joule per second is power. Remember, if you remember the equations, work is force times distance, right? That gives you the equation or the units for energy. And then power is work over time, or energy over time, joule per second. So what do we do for a rotating shaft? We have a torque, right, which is a force times a distance, and we have a rotational speed, right, which is some kind of something per second. And we use the rotating speed in radians per second. So how many radians per second? radians is sort of this, it's almost like this dimensionless value. So if we have something moving at 1750 RPM, right, that's revolutions per minute, we've got to convert that to radians per second to use this in the torque or the power equation. So we all remember, right, 1 revolution is 2 pi radians, 1 minute is 60 seconds. You can easily convert to radians per second if you're given an RPM. And so here's an example. Find the torque in the boat shaft if the drive shaft of the boat transmits 95 kilowatts of power when rotating at 525 RPM. So let's work that out. Torque in the boat shaft. I'll probably just stop after working this example out. All right, so what's our power? Our power is, well, we've got, let me first write the equation. Power is torque times revolutions per minute, or RPM, well, radians per second. Our power, we know, is 95 kilowatts, right? And that's equal to 95,000 watts, right? And we know that a watt is equal to a Newton meter per second. And we know that it gives us 525 RPMs. So let's figure out the, we need to figure out the torque. So torque is just going to be power divided by N, right? Let's figure out what N is. N is 525 revolutions per minute. We've got 2 pi, radians per 1 revolution. And we have 1 minute is 60 seconds. So this turns out to be 55.0 radians per second. That's our N. So our torque here is 95,000 Newton meters per second divided by 55.0 radians per second. And this gives us 1,727 Newton meters. All right, notice radians are sort of this sort of dimensionless value, right? Dimensionless unit. You know, they're just an angular. It's just an angular number. It's like 2 pi, right? This is 2 pi radians. It just goes away. So that's the one thing you kind of have to remember with torque. You want to get it into radians per second, the revolutions per minute, and then you can do the math this way. So you have to use radians per second. All right, I'm going to stop here, and let me just check something. Yeah, I'll just do this next. I'll start here next time. Next time we'll talk about power. We'll just start off with power again, but we'll talk about the U.S. units of horsepower and how they're just a little different than wattage and the conversion factor you need for that. All right, so that's what I got.